You are going to watch this video instead of attending class today. I want you to be able to have the opportunity to work through the group activity that you would have gotten to do if you were in class. Let me start with the announcements. To do after you watch this video, you should be able to complete Achieve number 10. It is due tomorrow night. This video is due tonight. Then you're going to finish preparing for Exam 1. Notice I didn't say start preparing, finish preparing for Exam 1. There is in the Week 5 module a page that is entitled Study for Exam 1. And as you study for Exam 1, it's going to have the learning outcomes that you need to work through, additional end-of-chapter problems that you should be practicing with, and it will also have a correlation guide posted if you are using the exam repository to do practice exams from there. It's not something that I really recommend as a study tool, but I know the students do enjoy working through those exams thinking that it's great. I would happily see you use the end of chapter problems as your practice, because I don't look at old exams as I write exam questions. I look at the learning outcomes and what has been assigned to you. But that's up to you. The play pods that you see there are not due until Monday night of next week, because that's what you need to do to be prepared for class on Tuesday. Please don't watch those prior to your exam, because it's a lot of rate law information that might get jumbled in your mind with what you do need to know. I would like for you to take a time to pause this video and go into the Week 5 module and find the group activity for today and open that activity up. I would love to see you either print it off or have it available for you to pause the video and reference from time to time as you walk through this activity to make sure you can write a rate law for a given reaction. We are going to do it for the reaction that you see at the bottom of this page. A rate law takes the form of a rate constant times the reactant. In this case, this is acetone. You don't need to know its name. Raised to some power, you're going to figure out that power. It's going to be Br2. Raised to some power, you're going to figure out that power. And when you have a catalyst, that catalyst also will have a power, and it'll be part of the rate law. So if you haven't done so already, go and open up the group activity, have it ready, and be ready to work through it with me and a lot of play posit questions. This will be your class participation grade for today. I have the data up there at the top of this slide, but you have it there if you've pulled up the activity. And for this activity, you're going to be using your notes, the example problems I worked for you in the videos you've already watched, and you're going to be determining the rate law eventually and the rate constant as well. So the first thing we're going to do is try to figure out the power of the acetone. Now I'm missing a C right in there. It's CH3COCH3, but we're not determining the order yet. I want you to look at those experiments and figure out which of those experiments you would use. The experiments are number 1 and number 5. If you did not get that, this is how you know. You're trying to hold the other substances constant. And in these two experiments, the Br is staying at 0.05 and the H plus is staying at 0.05. Now, we don't need experiments where they're always 0.05, but they are not changing from one experiment to the other, and that's the way you need to work it. So now, utilizing experiments 1 and 5, I need you to determine the order of acetone. What is acetone's power? In other words, it's CH3COCH3. It's raised to some power. We'll call it X. First figure out X, and then you'll know the order. Well, it is first order. You have seen the answer. First order in acetone. If you were not able to get that value, then you should watch this little demo here. So going from those two experiments, I usually do the large one over the small one. That's the ratio of concentrations. Those concentrations are raised to some power, and that would give you the ratio of the rates. So I have to make sure I'm doing it in the same order, which is experiment 5 over experiment 1. And that gives me 1.33 to some power, gives me 1.33, and the only value of x that makes sense is an x of 1, so that makes it first order. Now you're going to do similar work here, and you are going to figure out the order of BR2. First, determine which experiments you need to use those experiments, and determine the order. Experiments 1 and 2 hold the acetone and the H+ constant so that we can see how the change in concentration of Br affects the change in concentration of the rate. So that should give you a 0th order. We say it's 0 order. And if you did not get 0 order, I take the large over the small, raised to some power, which I called it y in this case, and that is, and you can see right off the bat, the concentrations are not changing, and if the concentrations are not changing, then this is, I don't know what I just did. Is there close? This gives me a value of 1 here, and this is a value of 2. What value do I need to raise it to give you 1? Well, any number raised to the 0th power gives you 1, so that's how I know it's 0th power. Now you're going to do the work for H+. For H+, it is again first order. Now, which experiments did we use to get first order? I used experiments 4 and 5. In experiments 4 and 5, we see that these are being held constant and these are being held constant. I take the large over the small, raised to some power that I'm going to call z, is equal to, and make sure you do it in the same order, 3.1 times 10 to the minus 4 over 7.6 times 10 to the minus 5. And that is a 4 raised to some power gives me 4. So z has to be the first power. Anything raised to the first power will give you the same number back. So now we have a rate law. The rate law is rate is equal to K. It is the acetone raised to the first power, and it is the H+ raised to the first power. Now you can take any one of those experiments and you can determine the value and the units for the rate constant. Hopefully you got that correct, but if you did not, here is the work. Rate divided by the concentration of CH3COCH3 times the concentration of H+ would give you the rate constant K. I have chosen experiment 1, so it's 5.7 times 10 to the minus 5 molarity per second divided by 0.30 molarity, and also divided by the H+ of 0.050 molar. This gives me a value of 0.0038, and one of these molarities cancels with one of those, and that leaves me with units of 1 over molarity times seconds. Last question I have for you is, sometimes we talk about the order overall. So what is the overall order of this reaction? It is second order overall. We add the the orders of 1 plus 1 to get 2. And I'm going to tell you right now, every time it's second order overall, these will be the units that always will have to come out, because you always have a couple molarities in the denominator to cancel. So that is practicing through determining the rate law and the value of the rate constant if given experimental data. Now, if you back up in your notes a little bit, where we're not dealing with rate law, but we're dealing with the rate expression, I would like for you to determine, this is an old exam question, which of those would determine the rate of this reaction correctly. So the answer is D, and here's what's wrong with all of the other answers. This one here for A would be correct if there was a minus sign in here. Since it is disappearing, this part is negative, and the rate must be positive always, so we need that minus sign in there to make it positive. The second one would be correct, B, if we removed that 3. It is a change in concentration of oxygen. There is no coefficient, so that's an assumed 1 there. And so if we got rid of that, it would be correct. For C, this one would be correct if we removed that minus sign, because we're going to divide it by 2, but not change the sign because this is appearing, so it's already a positive value. And NO has no coefficient, or a coefficient of 1, and therefore that makes D the correct answer. Okay, so now we're going to use that rate expression in this problem. We are given information about the average rate of disappearance of O2, and it's told what its value is, and then we're asked for the average rate of appearance of H2O, all right? So we're asked about this one. This is the one we want to know when we were given information about this one. I'm going to get you started, and then I'm going to let you stop and figure out the answer. We know that the rate of this reaction could be done in terms of oxygen. It would be a negative change in the concentration of oxygen divided by time, the rate of change with respect to time. But to make it the rate of the reaction, we have to divide it by 7. We could do it in terms of the oxygen, in terms of the water, since we're being asked about it. We can do it for any substance, but for the water, it would be the change in concentration of water with respect to time, but divide by 6. Now, when they are telling you the rate of disappearance and giving you a positive number, it is disappearing, so its change is negative, but we say that it's disappearing at a certain rate. We're giving you this component. We're giving you this part. And we are asking for this part. Okay, this is what they want to know. How fast is the water appearing? So use that information and obtain a value, and then once you have an answer, we'll check our work together. Now, if I were to put in to this, where this box is, the 0.49 molarity per second, and multiply by the 6 to get the 6 over there, I could solve for this part, and I would get the answer of this problem. And it is 0.42. I'm going to show you another way to work this problem, okay? If the rate of change of O2 is 0.49, that's the molarity of O2 per second, and you don't want the molarity of O2 per second, but you want the molarity of H2O per second. we can look at our balanced equation and find this ratio. And in front of the O2 is a 7. In front of the H2O is a 6. And that is going to give us that 0.42 molarity per second. I didn't do anything with the molarity. The second, it's still sitting there. I'm just changing my moles per liter. They're in the same container, so the volume's not changing. And this is another way of looking at this problem that I find a little bit easier. The answer, oops, sorry. Okay, now you've got another old exam question that you are going to determine which of those is its rate law. So now you know that the answer is A. If you did not understand why the answer is A, then you can watch the video that I'm going to, just the explanation here. In order to figure out NO's concentration, we need to hold H2 constant, which is experiments 1 and 3. We do a ratio of the rates. This would be 0.20 divided by 0.10 to some power. And that is going to give you a ratio of the concentrations, which is 4.92 times 10 to the minus 3 over 1.23 times 10 to the minus 3. That is going to give you 2 to some power, gives you 4. And that tells you that the X is equal to 2. For the other substance, I'll change colors here so that we don't get confused within it. I am going to hold the NO constant, which is experiments 1 and 3, and see how changing the concentration of H2 affects the rate. So again, and I'll do this here underneath there in red, we'll have 0.20 divided by 0.1 to some power, I'll call it Y, is equal to 2.46 divided by 1.23. Now it's both times 10 to the minus 3. Those are going to cancel. Just not going to write it all out. So 2 to some power gives you 2. So you would have a Y of 1. All right, so that is your lesson for today. And I will see you in class on Tuesday. And make sure you look for the announcement that shows all the extra hours I have for you on Wednesday.